Hey everyone, let's look at this idea. During the California Gold Rush, during the California Gold Rush, many small towns grew at incredible rates as people came from all over the country in hopes of finding gold. One small town had a population of only 35, but once gold was discovered nearby, this population doubled every month. All right, well, let's think about this relationship. It seems like a relationship to me. It even seems like a function, right? Population is changing every month. Seems like the month is going to be the input. Seems like the population of the town is going to be the output, right? So it seems like it's a functional relationship to me. So is this a linear relationship? Well, let's find out. What's the initial population here? The initial population, or let's call it the initial value, let's stick with that vocabulary term, is 35, right? For our population, the initial value is 35, right? What about population? What about population after 1 year, right? Population after 1 year. Well, after 1 year, the population is going to double, right? So after 1 year, the population is going to be 35 times 2 equals 70, right? Okay. What about population after 2 years, right? What about population after 2 years? Well, that's going to be 70 times 2 because the population is going to double again, right? Which is going to be 140. Oh, whoops, I shouldn't be saying years. This is months, right? My bad. Let me correct this. This isn't year. This is not year. This should be months. Sorry about that, everyone. Let me amend that mistake. 1 month, 2 months. And what about population after after 2 months, after 3 months, right? Population after 3 months. Well, that's going to be the 140 times 2 again. It's going to double, right? And we're going to have 280 people in that town after 3 months. Okay, so we can tell already this is not a linear relationship, right? Because the output, I shouldn't have a question mark, it should be an exclamation point, right? This is not linear. Is this amount changing every time from 35 to 70 to 140 to 280? Clearly it's not changing by the same amount each time, right? Okay. Is it changing at some kind of like rational rate? Is it changing according to a rule that we can identify? It looks like it is, right? It's changing by a constant factor, right? It's changing by a factor of 2 each time. Instead of adding the same thing each time to get to the next value, we're multiplying by the same thing each time to get to the next value. We do have a word for this kind of relationship. We call this a geometric. We call this a geometric relationship. We call this a geometric relationship. And instead of a common difference, it has a common ratio. Has a common ratio, which in this case is +2. So hopefully we also remember our next now equations for writing arithmetic sequences as recursive. Well, we have the same thing for a geometric relationship, right? But in this case, instead of adding the same thing each time, right, we're multiplying by the same thing each time, right? So for example, if we wanted to write a next now equation for this relationship, to find the next term, to find the next value of population, you take your current term or your current value of population and you multiply it by 2, right? Can we write that as a recursive sequence also? We sure can, right? Or rather a recursive function. We can write f of n plus 1, right, equals f of n times 2. All right, so let's look at this. An extremely successful business is growing so quickly that its revenue is tripling each month. In its first month, it had a revenue of $250. All right, is this a geometric relationship? It definitely is, right? This is definitely, let me get my brush back here. This is definitely geometric, right? Because, well, let's look at our information. The revenue is tripling each month. So from the first month, what would you do to find its revenue in the second month? You would multiply by 3, right? To find the revenue in the third month, what would you do? You'd take the revenue from the second month and multiply by 3, right? So we know this is a geometric relationship with an initial value of 250, right? And what do we call it again? We call it a common ratio, right? A common ratio, when it's geometric, a common ratio of positive 3. Because our value is tripling each month, that means to find the next term, we always take our current term and multiply by 3, right? So if we wanted to write this in next now form, right? We know that the next term, or the next value of our sequence, is always going to be our current value times 3, right? How could we write this recursively? We know that to find the next value of our sequence, right? We take our current value, f of n, and multiply it by 3, right? Or we could write it like this, which I think you all can notice means the exact same thing, right? To find the next value of this function, you take the current value of the function and multiply it by 3, right? Can we find some values of the function? We know that f of 0 equals 250, right? Can we find f of 1? Well, what are we going to do? We're just going to take 250 times 3, right? So f of 1 would be 750, right? F of 2. F of 2, well, we're just going to multiply by 3 again, right? Get 2,250. F of 3, how do we find that? We're just going to multiply by 3 again, right? And get 6,750. F of 4, what are we going to do? We're just going to multiply by 3 again and get 20,250, right? So you might notice that this is growing outrageously quickly, right? And that's generally how geometric relationships go. When you have a common ratio which is greater than positive 1, you're going to grow, you're going to end up growing real fast. If you have like a 1.01, okay, it's going to take a while to get really fast growth. But even then, you're going to get there eventually. But if you have a common ratio, say like 2, 3, 4, you're going to grow incredibly quickly because when you multiply by the same thing over and over again, your value very soon, if it's even a slightly large number that you're multiplying by, is just going to skyrocket in growth.